measurements of the movement of air masses. So air masses are moving around, and we have this data set just with the sensor-based data which were collected like a long time. I'm gonna plot it just to show you something. Take a look at the results. This is a time series, a very complex time series, very difficult actually to learn. You can try, like I swear, you can try like logistic regression, you can try distance weighted nearest neighbors, you can try any. When I say any, it is indeed any statistics technique, like the ARIMA models or autoregressive models, moving average, whatever. It doesn't matter. You could use anything. But instead of working on that particular space, we could translate that space to something else. And that's the point. I mean, it's not just about the algorithm. It's about the space you give to your algorithm. So if I try to change the space of that algorithm, and maybe I can show you something about that in the next talk, maybe, I don't know. Take a look what I'm doing here. I'm using a very simple theorem from mathematics, from dynamical systems actually, that every time series value is going to be associated to another time series value 5 time instants in the future. Take a look at the series. If we have like the first, I don't know, 20 values. Take a look. This value in here, it's the same as this one. And 5 instances ahead, 1, 2, 3, 4, 5, we have this value, which is in here. In 5 again, a long time, we have this, which is the same as this one. Take a look what happens if I plot this data set to you guys. Maybe even better. If I plot like this, 3D, yeah, I'm gonna plot using line. It's so beautiful. I don't have it here. I did install it. Okay, no problem. So I'm gonna do it again here. No problem. Series, read table, lore 63, first dimension only, T-series chaos, and now I'm gonna embed it using these dimensions. I know they're gonna work. Of course, I can explain you guys how that works later. And now I'm gonna plot it. I'm gonna plot it using just 2 dimensions because I don't have the right package here to show you guys the 3rd dimension. Take a look. Take a look, Hardy. This is the space I get. Something very complex we had at the beginning, but now we have a very, very nice and smooth behavior. And on top of that behavior, I can build like lots of Gaussian functions along those curves and compute a regression for any sort of time series. So I would say something like that. You can use DWNN to make regressions on any kind of time series. Could be like a sinusoidal time series, could be a logistic map, could be a Lorentz system, could be anything. And you can use the K nearest neighbors algorithm to perform classification. So if I separate both, I'd say something like this. Let's get back. I'd say something like this. If we have DWNN here, we're gonna use it to employ on time series to make regressions, perform regressions or data streams. KNN, classification. Multi-layer perceptron could be for both. I don't know, what else? C4.5, like the decision trees, that's much more for classification. So we have like techniques which are much more oriented to tackle classification problems or regression problems. But both take advantage of the same theoretical foundation I provided today. We don't have like that, I mean, that much of time to show like lots of things, but we can schedule like another talk. I think that's interesting. Let me see the second. Okay, theory will be applicable to cardiovascular risk prediction analytics. Yes, actually, that's a very interesting question. That makes me remember a paper in Nature where a guy decided to get some brain sensor information and reconstruct that sensor information, and he observed that every time someone is more like likely to have seizure or seizures a long time, that shape in the space is going to be different. And so we have like a normal patient and a patient that's prone to have, or is gonna have like probably not now, but in the next like 5 years, some sort of seizure problems. After reconstructing and performing the regression functions are going to be completely different, and we can take like theoretical decisions on that to classify if a person is normal or not. And in terms of cardiovascular risk prediction, we can do the same. Yes, we can do the same, because every time we have a cardiovascular data, we're going to have like something that's very similar to a sinusoidal signal. And when that sinusoidal signal changes abruptly, the space where we are inducing our regression function is going to be completely different. It's going to change a lot. So a normal patient is going to have like a very nice elliptical behavior. And if that person has some sort of problem, is going to have some small rounded elliptical functions that are smaller inside that bigger elliptical function. And that happens. Like I've done some studies on that too. Yeah. So you guys, yeah, you can ask, like shoot it. Yeah. I think it'd be very nice to show you guys something about like time series prediction, data stream prediction, how to build up regressions and also classifications. I mean, it's very nice also to implement things on the fly. Like I love implementing like multi-layer perceptron. I've already implemented the convolutional neural networks from scratch, like while filming. It's got it's necessary like a long time to do it, because like 3 hours 4 hours, because it's not easy. It's got like several very important theoretical points that I should mention, but I'm here, and we can like decide together what's nice for people in this group. Is that all, guys? Hardy, is that okay? Could you listen to me? My voice was good enough. The screen was good. Okay. Can you say that DWNN is particularly superior for 2 or more variables that have clearly multinomial distribution of errors? As we are using Gaussian functions, and Gaussian functions have this symmetrical behavior in terms of the central point, of course we are much more in favor of spaces that follow that sort of behavior, that have this sort of a normal distribution along the space. And if we have like a multinomial space with lots of regions with that sort of Gaussian behavior, yes, it's going to be better. It's going to be way better. A linear regression is always like, yes, a linear regression is much more to separate a space like that. So every time I have a linear regression, I'm doing something like this. I'm just crossing the space like that. So I have something on one side and something on the other side. So we have like a barrier here, a hyperplane. When we have a Gaussian, it's going to be something rounded, let's say, and we are defining a different bias. That's much more, that's something a little more deep, but I'm going to say anyway, a little deeper. We are working with a second order polynomial space. We are working, instead of a linear behavior, we are working with a more complex space that's capable of representing much more complex scenarios. Yes, it is capable of representing more complex scenarios than a simple linear regression, of course. But of course, if you have like a multi-layer perceptron with a bunch of hidden neurons at the hidden layer, you can mimic the same behavior. You can mimic the same behavior as having a single Gaussian function in the same space. Yes, yeah, you can do both. Yeah, more questions, guys. Yeah, just we're just starting. Yeah. Well, thank you very much for the yeah. Thank you very much for you too. Yeah, some guys here just thanking for the talk. We still have like 11 people here. I see some familiar faces. Yeah, that's quite nice. Quite nice indeed. Okay, no question. So guys, thank you very much. Thank you very much. I'm gonna leave the talk in the group. So anytime you have like questions, could be theoretical or practical questions, just ask me, just send, and we can discuss. We can talk about some practical stuff too. I know we are much more driven by the practical things, but as a matter of fact, if we don't know that stuff, that theoretical stuff, oh, thank you very much for you're speaking Portuguese now, Hardy. That's quite nice. And it's I know it looks like very that's boring, that's very theoretical, that's not nice, but it's the opposite. If you guys are working with deep learning, I can show you, for example, okay, you're doing something right here, you're doing something wrong, just because you don't know the basics about the theory. And that's important. That's really important. Guys, thank you very much. Hope to see you again, and anytime you have like questions. Oh, thank you, Bruno. Thank you. Just send me, okay? Thank you, Tanai. Oh, very nice of you. Very nice, guys. Thank you very much. 12 people, yeah, it's increasing now. Better, getting better. Guys, see you next time, okay? Bye.